Right,
Dude,
folks. All right, the thing has been hit. It says we're live. Hey guys, what's going on? Memes here, and I am joined today by PhD student Michael Hughes. Say hi to the folks, Michael.
hi. And
All
so,
right.
yeah, that's
Now,
it.
now, is it all right if I give like our deep lore about how kind of
Yeah,
how we came across each other?
uh, yeah, please. I think it's good to set the stage, as we were just saying. Yeah,
Okay. So ultimately, full disclosure, both Michael and myself, basically, we are on the Demystify Science. Shout out to Anastasia and Shiloh over there. And basically, at one point, I came in. I'm one of the Patreons and everything. Shoot them a few bucks a month because I like what they're doing and everything. And I think folks should support each other if you happen to have the means. Personal opinion there. But Michael was talking about like water and like ice and stuff like that. And I had just recently come across the Lieb ice constant on Wolfram, which has to do with basically square based lattices with like wraparound and everything. I'll post, I forgot to post the links to the additional things there, but you were talking about that, and we just kind of like hit it off. We were going to do a chat, but the scheduling and everything, you only had so much time, but we did have about a half hour or so, like really good, deep chat. And life got in the way. And now we're here talking about some of your work, what you've learned about water over the past several years, because you've been studying this from all different angles. And I think it's very important that folks can kind of broaden out where you're looking, just because personal opinion, there's a lot of specialization out there. It's helped us enormously. The only thing that can happen is sometimes I feel like, in my opinion, some of us we might get tunnel vision. I know I do all the time, and that like I can get really hyper focused on things. But if there's other things out there that legitimately might make my job easier, even if I find something I'm like, oh, that was wrong. Like the other day we were trying to do a calculation. It's like, oh, it's HT. Oh, what is that? It's like, oh, obviously it's Henry's Tesla. And we're doing the calculations, and we spend probably about an hour or so going through all these things, actually finding answers for all these things. It's like, this doesn't make any sense because I'm putting it to Wolfram Alpha. I'm like, no identify or define dimensions. It's like, it'll show the number of dimensions, but it's like, this isn't defined. I'm like, well, why is this on NIST? Why is this a codata constant of nature here? So ultimately, I think it had to do with some ratio between magnetic moments or shielding of like protons versus tritium, and then like protons. No, excuse me, hydrogen versus tritium, and then hydrogen versus deuterium, and everything like that. And it's like we do that, and it's still. I found a paper from Kodak from 2010. And it's like this is this here. This is this like H hydrogen. Duh. I thought it was Henry's or Hertz, and I was totally wrong. And then T is basically like the transfer process, or T is tritium there, and then HD, hydrogen deuterium. And we spent all this time. It's like, well, we were obviously wrong. But if you're doing research, if you're trying to get a little bit closer to truth, if you would, shout out, um, I think we need to have a very broad perspective. And no one person can know everything. I just know that you've spent the past couple of years doing a lot of research on water. My soliloquy is over. Michael, let us know what you got going on.
perfect. Thank you for the introduction. And yeah, so my background is I did my PhD in protein structure and structural biology, where I got into this field of basically liquid-liquid phase separation, which is kind of this thing that was observed and was going through this around like 2012, 2014, where a lot of cellular processes, like you might wrap a cell process in an organelle in a membrane like the mitochondria or the DNA in the nucleus. Right? But there's another thing that the cell uses where it's a phase separation, almost like water and olive oil, only except that it's water on both sides and it's like proteins or RNA that are enriched in one phase or another. And so we have these situations where we get this like spontaneous demixing of molecules in the cell. And this is how you like might start a reaction, right? Like the temperature changes and suddenly you have like your heat shock proteins do something. Right. And so I was like, man, what's regulating this like a new apparent like really important use of phase separation that's governing a lot of cellular biology that is now like becoming apparent as we get better at measuring stuff. And so I happened to like come across this, and in my like desire to understand phase separation, I just kept reading papers and realizing it like the solvent, the water must be like important and playing a role. And so then this kind of got me onto this thing where to try and understand protein biology, I suddenly had to understand the water that was touching, right? And I was always looking at pictures of proteins and ignoring the water around it. And so then I just started to spend like 3 years reading physics papers, chemistry papers, all these different perspectives on water and how it's like these odd things that these different scientists are measuring in their systems. And again, from this like multiple perspectives now, it's like interesting to reconsolidate after we're so siloed to like bring it back together. And so what I've been trying to do, and I have, I have some slides. I'm not sure if people do PowerPoint, or you just like maybe to like talk through it, or what you just prefer is.
Oh, no, no. If you got something to share, I mean, I'm just looking up different things, trying to learn from myself. Please
Yeah.
learn me as much as you can.
Gotcha. And yeah, I'm sorry I had this conversation, but I'm curious, like, how long should we talk for, and about like what level? I'm curious.
Wherever the conversation takes us, you can go into as much depth as you want. I will stop you I will let you speak, and then I will ask what the heck you were saying.
Okay, that's perfect. Yeah, that sounds good. So feel free to speak up and drive it anywhere you want to go. But what I effectively or ultimately came across was through reading all these papers was my own idea of like a model of water that I kind of developed that I like borrowed from as many people I could read in like the past 60 years and piece it together. And then how this like model of water might show up in interesting like biology. And then my personal question that I'm like wondering about and trying to like get more at, and so I'm putting out there in hopes that something interesting comes back to me, is what is electricity in water? What is charge in water? And this like matters. Of course, we use like bioelectricity for nervous system stuff, like everything that we're doing. And so at the end of phase separation, when I like was interested in protein science, and that led me into water for phase separation, and now I'm trying to understand water phase separation, it runs into electricity inherently, it seems. And so that's where I hope to like leave the conversation, right? Is like share my water model, and then talk a little bit about electricity and water. So
I mean, I'm totally, full disclosure, I'm totally biased on this. I think
appreciate it.
charge is taking care of a lot of stuff and things.
Oh, so okay. And I think that this is what's kind of curious to me is I have no horse in the race. I just kind of read papers until I came up against problems I couldn't solve anymore. And it was always electricity and magnetism. And it always seemed like at the end of the day, a chemical bond is a sharing of charges between things, right? And so
I mean, I have to get that out of the way because I am totally biased because I have said some of these things previously, not knowing what it was. And I just kept asking the question again and again. And ultimately, a lot of times it just seems to keep boiling down. It's a fascinating thing. And that's why I want to learn more, especially if it has something to do with water. Because as Rick has said, water is it's a heavy subject.
water is a heck, it can be. I like it. So now I need to ask, is there an
If
easy
you
way
go
for
down
me
to
to
the
present?
bottom here, you'll see a button
Yeah.
that says present. If you hit present,
Yes.
if you want to upload something, you can do that. If not, you can just do share screen. And
Okay.
if you share the tab, it will share audio, or you could just share a whole window if you wanted.
Okay.
So if you just
Rad.
bring it up, if you have like a PowerPoint or something, I would click share window. And what that will do is you can then select from the options your PowerPoint.
Okay. Select from the options in my PowerPoint. You mentioned something about audio. Should I be worried about something when I'm presenting or sharing screen?
I just select window. I'm getting a little bit of feedback. I'm not sure if speakers are near the mic.
Yeah, I think that's the issue here. Okay.
I'll lower myself down a little bit. Got it. Still getting some feedback.
Yeah. See, let me ask, what's the fix for feedback? The easiest one, real quick.
Maybe you exit and come back in.
Okie doke. Let me try that real quick.
Let me see. Did I change my things?
All right. Yeah.
All right. Oh, that seemed to work. There we go. The beauties of live internet, folks. You never know what's going to happen. And I should totally reuse my content and then actually just touch this up, show the specific things, and he's back. I know. Oh, seems better.
Okay, hopefully. Let me know if it goes wonky again. Yeah.
No, I got you. Chat will let us know.
Perfect. Perfect.
There we go.
All right. Radical. So,
What are we looking at?
um, so use slideshow for beginning. All right. Everything looks pretty good. Actually, does everything look pretty good?
I realized my mic was I made the screen bigger so I could see it more, but I
Yeah.
then was my mute button was not in the way, and I don't have a hotkey because I'm a terrible host. So yes, looks good. Take us away. The audience will probably have some questions along the way, so they seem
Perfect.
intrigued.
Yeah, excellent. And so yeah, title of what I'm gonna ultimately be talking about is what is the electric charge. I am a protein structural biologist by training, so I like to do protein art occasionally in my free time. So this image on the side is a receptor with a molecule in it, and I like to do a lot of visualization. So I share that, play around with that.
Wait, I just think I saw a hexagon, sir.
Maybe.
I see it too, and they're sharing.
Yeah, I think that this is the THC receptor, and this is a THC analog that's bound to it. And so I download the protein structure files and import them into a 3D modeling program. So this is just a small molecule that I think
So
looks
that's
like
how that
THC.
works.
And
Cool.
so, yeah. So what I'm going to be talking today a bit about is to get to what is electric charge in water is a kind of short review of water and structure of water and diffusion of water by going over some like anomalies that water has and this concept of two-state water to explain them, and then how water moves through a rotational jump model and its hydrogen bond network. And I'm going to propose that the water hydrogen bond network is altered by solutes and surfaces, and this is the equivalent of osmotic pressure when we talk about osmotic pressure. And that is my second proposal, is that electricity can be stored in the altered hydrogen bond structure, right? And so what I'm effectively saying is that when you pour something like hydrochloric acid into water, because that's a solute, the hydrogen and the chloride surfaces change the osmotic pressure. And then this is kind of how we store water in the altered like structure. And so now you have like a different pH, and this is a different like voltage, and this can do work upon its like attempt to return to neutral. Right? So that's kind of like the overview.
So just to refresh, osmosis. I remember something about that was the process by some water will flow from like some either saturation level pressure, some random thing I don't. I just remember when we got to osmosis in biology, it just seemed a little dry for me, and I kind of like zoned out.
Totally fair. I had the same too because it's kind of nebulous, but yeah, osmosis is the general concept of water moving from like a high concentration or to a lower concentration of water.
I mean, I'm like, okay, what are you saying here? I'm like, okay, duh. It's like this. Why are we talking about this? And it just seemed
Right.
to bore me, so it lost me. But apparently, there's more to it now,
So I
or we
think
know more.
right, you're getting the exact issue that I had. Is like it seems like so apparent. I didn't know why we had to like attach a label and spend weeks learning about something that seemed like obvious from the get go. And what's like curious is that what I learned is that not all particles are the same. And so for sometimes in chemistry, there's these things called like colligative properties. And colligative properties, from my understanding, are like no matter what you have dissolved in the water, it's just a number of particles that matter for osmosis, like what attracts the most water. And it turns out that's like completely not true, right? Like if you're like looking zoomed out macroscopically, all the water is kind of like perturbed by these particles. But if you zoom in, the kind of particle you are changes things differently, right? And of course, this matters. Like sugar water behaves differently than salt water, right? But yeah, this becomes really apparent. And so I think that osmosis and osmotic pressure is taught without like the appropriate frame to make it interesting for us to care about. And hopefully this throws that out.
So that's very interesting because it's like, see, for me, a lot of times I think it's like, oh, well, water is water, but it's like, all right, water also has a lot of interesting properties and everything, and depending on, like, at least from our view, it's like, okay, we got water. Water might act like water, but if there's other things within the locality of that water, what might that do?
Bingo. And it turns out a lot. And that's what I kept finding. And that's why I'm so like interested in this and trying to share it. Uh, and
Groovy.
so, yeah. the first thing is to talk about some like water anomalies. So when we talk about like, ideal physical scenarios or ideal solutions, ideal, right, like a spherical cow in a physics problem, or like a frictionless kind of assumption to start with. Then we have like our ideal, solids and fluids. And the concept here is that water is a really anomalous liquid, arguably the most anomalous. So the first thing is that most things, when they freeze and get solid, they sink like benzene or almost any substance. But when water freezes, it expands and floats. So there's this weird thing here where at 4 degrees Celsius, water is its densest. But then every degree you get colder, water's density increases and it starts to float. Right. And so this is the only, like, water is one of the few substances that does this. What does that like kind of mean? Another thing
What was there? Because I actually looked into this not all that long ago, and because here's the thing, I think it was like typically at like 4.2 degrees Celsius according to like some 1977 poster from, because it's weird, they listed as one, well it's this, but it's this because it's right about or perhaps exactly at some particular temperature and pressure, like was it 1,000 kilograms per cubic meter, and then like was it 1 gram per like cubic centimeter. So I'm like, oh, that kind of sounds like the metric system. I think we kind of based it initially off of that, which is an interesting
Yeah.
thing.
So I think this is kind of fascinating. I'm not quite sure if it's what you're getting at, but I always wondered, like, if I one time asked a friend engineer, like, what's the definition of the meter? And like, so let me ask you this: what's the definition of a meter? Right.
It's, well, to be fair, they actually redefined it recently. I believe it's on some computation of like the Planck. It's basically defined from the constants of nature. I want to say like some iteration of the number of Planck masses in it of itself. Um, I actually honestly don't know. I just know it's derived after we take the constants of nature to the best of our calculations, and then we run it through. Because well, that was one of the things. Because when I had come here, I had actually noticed. I did one of the calculation in Thad's book, and I looked at the numbers. And I'm like, wait a second, these numbers deviate. So I looked in and looked into it because I got the number that Thad had, but and then the numbers differed. But then I looked. The definition of the numbers had changed. They had swung by like a decent bit, like outside the error bars. So I'm like, what was going on in 2019? A whole bunch of smart folks got together, and basically they just started the SI redefinition, which started in 2019, and they rolled it out through 2021. And one of the things you notice is, I think, according to that, he said some of the things swung by about like three and a half sigma. So it's like I think famously, what was it like the radius of the proton or something like that. It's like, well, we think it's like 8.2, 8. Oh, it's like 8.6, 8.7. It's like, oh,
Mhm.
well, that seems to be a fairly significant difference there because you only have like a couple of digits of confidence in there. So it's like, and I noticed like for H and H bar, they went from 12 significant digits with like a decent error to they just lopped it off after 10 significant digits. They're like, at this time, this is what we believe we have the highest level of confidence in. So I'm like, that's cool, but it's a hard thing because if you adjust one thing, that's going to propagate through, and you don't want to break the system, but you also want to be accurate and everything. And I think it's they're going on, I think, 5 years from an update, and like there have been better measurements and stuff like that, but I don't
Yeah.
know. We'll see.
We'll see. No, it's fascinating. I didn't actually know about the recent story, but then before like this redefinition, my understanding is defined by according to like the speed of light, right, as some fraction of the speed of light. And then the question is like, was the speed of light or the meter invented first, like discovered first, whatever you want to call it, right? And then the answer like is most likely that well, we had like a meter in the 1700s, and when did we first like measure the speed of light?
the,
And
the, the
so
distance of the North Pole to Paris divided by this. Yeah, it was
bingo,
great. Like
right.
we pick something, but once within the metric system, the beauty is there's a coherence. So once you pick and define something, the other units relative to them will be combinatorically
Right.
equivalent,
And
and
so
that
it's
will
somehow,
adjust over time.
yeah. And so because this is equivalence of water weight to the meter, right, there's got to be some equivalency of this process to defining like weight of water, yeah, through the story somehow.
It's a
And I don't know,
fascinating thing.
right, I don't know what it is, but like these measurements are inherently tied together in their definition somehow and just the origin of where it like came up from. And I don't really know the story, but I'd love to one day. Yeah, but I think, yeah, you said something that started me off thinking about that. And like, yeah, it's the right questions to be asking, like where we get these definitions and what they mean and why they're tied together. They're like cool relationships there.
You're sounding like a philosopher, sir. I love it. Continue.
Thank you. No, I wish that they spent more time on the philosophy part of yeah, the PhD in biochemistry. There's a very light on the philosophy of the doctorate. Yeah, but another thing that's weird about water, in addition to this density anomaly, is the boiling point anomaly. So if we have like if we just go down, and we're just putting hydrogen, as many hydrogens as can fit on oxygen, sulfur, selenium, all down the eighth group of the periodic table of the elements. You can see that overall, like as you get heavier and bigger, you should increase your boiling point. But water is abnormally high to begin with. And so water's boiling point tells us that water is holding on to itself a lot more strongly than most other chemical compounds are that are comparable. And the most comparable chemical compound. Oh, go ahead.
Oh, no, 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 no. I'm just like, huh?
Yeah, it's and
That's
so the
rad.
most common thing we compare it to is hydrogen sulfide. So just sulfur with two hydrogens, right? They're pretty similar, but water's boiling point is significantly higher, which again indicates a lot stronger bonds between them, and also slower diffusion. So this is from a paper in the 1980s, and it's got my favorite abstract ever. The whole abstract reads, self-diffusion measurements in liquid hydrogen sulfide along the coexistence curve are reported. The results are compared with similar measurements in water. The anomalous behavior of water is thus made experimentally evident. So a nice 2-sentence abstract, which is telling us that they measure the diffusion rate of hydrogen sulfide, and then if you plot that and compare it to like what water should give you, it's this straight line is the expected diffusion speed, but this curved line is the actual measure one. And so at temperatures that life exists at, these like lower temperatures below 398 Kelvin, you get this anomalously slow diffusion of water, right? And this again is kind of telling us that the bonds are really strong between water compared to nearby chemicals that should be similar.
So this is the logger. Oh, could you just go back for just a
Yeah, yeah,
second? Like what is the okay? Oh, that's three. Okay, now I can see 396 Kelvin.
yeah. Totally
Okay, and it's
obtuse
given.
measurements for this
No, no,
day and age.
I'm trying to like if I saw like 273, that would stick out to me or something like that. But okay, so what it's saying like as water goes down, that's as the temperature decreases. Is that like like an unexpected density increase?
So at low temperatures, water diffuses much slower than would be expected if it just continued the same trend from higher temperatures. So it's almost
So
at like
water
this
has a habit of sticking together.
bingo. And like what's odd is that there seems to be this like phase transition here at low temperatures where this is evident, where at higher temperatures it isn't, right? And here it's like the same all the way through. So it's like this separate phase emerges at temperatures that light particularly hangs out at.
Cool. That's
Uh,
very interesting.
right? Curious. So we're just kind of collecting these like water anomalies now. And so then what they're all kind of pointing us to is that the bonds between water molecules are really strong. And this is because of the hydrogen bond. So what we learned is that water molecule has, the water has like pretty low mass. Just oxygen's weight is like 16 Daltons or units, and then hydrogen should be 1 each. So the mass would be 18 total, but oxygen is the vast majority of that. So this little bit of like 1 pound of your 18-pound total weight is like sprung out for these sides. So this gives you a small moment of inertia upon rotation, right? Because now you have this mass that's hanging out off the side, and it's just a really small amount compared to your really heavy center. But then if I like weight these squares, not by their mass, but by their charge or the dipole moment. So because oxygen is so hungry for electrons, the hydrogens, the electrons, they hang out more around the oxygen. And so this makes oxygen slightly negatively charged and the hydrogen slightly positively charged. But because it's equal, the charge transfer across them, the hydrogens are about as charged as the oxygen is, like relatively, but they're far less weight, right? So there's this really strong dipole moment. And what this is telling us is that water is like quite light, but its bonds are like way stronger than its like sprung mass is. And so this makes rotation really interesting because it's really like light and easy to rotate with the moment of inertia, but the bonds it forms between the charge centers of oxygen molecules are really strong. Right? So our bonds from this charge difference are a lot stronger than our mass differences. Does that kind of like add up?
So basically, it sounds like you have less mass. That if we were going to think of it, yeah, the billiard ball or whatever,
Mhm.
just height, whatever force, if you want to think of it that way, out there banging against things. Yes, it has a very strong charge, but the mass in of itself, it almost seems like it's a little bit tighter and seems optimized to kind of like, I'm just imagining if those things are there, if you got, all right, a slightly more charged proton and you've got like the same charge, but you don't necessarily have as much inertia. So it seems like it's optimized for something. I'm
Exactly.
struggling with the words, but continue.
Yeah, and I kind of struggle with them too, right? Because this like paints an idea, but we don't really know like where it leads yet. But the general idea is that like water has got this like rotational moment because it's got these like hydrogens that hang off and gives it this like weird mass thing. But that those are really light. But the hydrogens themselves, they have these super strong interactions. So while water itself is like easy to rotate by mass, it tends to stick to itself by charge, right? And that dominates its kind of desire to rotate. So it's always this like tug of war between these two. Right?
It
And the,
almost seems like I'm sorry, but it almost seems like it's not necessarily viscosity, but it seems to be doing something like that. Like it kind of like wants to stick together. And just Rick was
yeah,
commenting that
right.
apparently, uh, go on.
And so this is like looking like a spin glass or like a quantum system where you get these like moments of fluctuating coherence, right? Or would do
Okay. No, no, I can kind of, again, I haven't spent all these years studying it. Like I said, I mean, I think osmosis kind of just, that's stuck in my mind. Oh, water boring and everything. And the more I hear about it, especially like with these newer measurements and everything like that, and you see how these different things are connected, and once you start to hear a lot of the story and everything, because like Rick also pointed out, was it Archimedes or something like that? Like the whole legendary Eureka, he's in the bathtub. It's, oh, look, displacement and everything. And then like, things will float on water. That's really weird. So I could use that to kind of measure like, is this gold crown actually gold? Because he could kind of like measure the density, and like that's a very interesting thing there. But Rick is saying maybe you could comment on this. I don't know about, but H2 and O2 are the highest energy density for rocket fuel, or I think that's things that have been used before. So,
um
or would
so
something like that
can
make sense?
was
Whether or not that's true, does it make sense?
okay yeah, I guess
Different
I'm like
engineering. No,
I'm
no, no, don't
struggling
worry
this
about it.
because I did like look into a lot of like I love like learning about like rocket engines and why like different rocket engines and fuel types have their like ideal things and stuff. And I think that from my understanding that like hydrogen and oxygen is like very like it's the issue is that you can't store them like as dense like oxygen and hydrogen stored together is like just takes so much like volume or something or has to be kept at a temperature. But and so I don't really know about its like uh, density of energy versus its like practical implementation and where my knowledge like leaves off on each of those. So I feel
No
like they're
worries.
like cool questions and I think about them, but I wouldn't be able to like give you a good answer.
It's not your area of expertise. No worries.
Yeah. But I do like that
I,
area.
I, I didn't I didn't see a quick answer, but I think it's one of those things where you gotta keep them
Yeah.
separated, or else
But
then it's
this
yeah.
is, but I think that I feel like yeah, Gentleman Rick that referred to or said what is interesting though in that I'll get to that this is kind of like hinting at is that water is kind of like composed of two different phases and its idea is two-state water. So where water can store a ton of energy density is within going from like a low density ice or to a high density ice, right? Like if you put enough pressure on water to collapse it down to a different density, you've like put a shit ton of energy that can like spring out, right? And so you can, in the structure of water, the like hydrogen bonds between them, store a lot of like energy kind of in this way. And it can be really dense. And that's actually like a lot of the remarkable weirdness that is being appreciated now is how dense that energy can be stored in like in a small number of water molecules, just to kind of their geometry as opposed to like chemical bonds.
Now is that kind of like the whole like I remember learning that about super saturated solutions before, where as long as you're doing it like slowly, like I think across some gradient,
Mm.
but then one basically what is it like if something is boiling and you put like a whole bunch of sugar or something in it, like if you slowly cool it down and then you drop one thing of sugar, the entire you'll see all this crystallization. I just remember seeing something cool like
Yeah.
that back in the day.
So I love that experiment because I also remember that. And what was odd about like every year of my PhD and study was just like the realization of how that matters because and how this shows up everywhere. Because I study neurodegenerative diseases and the proteins involved in like amyloid diseases like Parkinson's or Alzheimer's. And what happens with those is you have these proteins, and at a certain point, they stop behaving well, and they form these protein fibers that are found like the neurons and the of patients with this disease. And what it is that your body is entirely that supersaturated sugar solution. And if you give it the wrong thing, the proteins will fall out in this, fibrous state that is not
Now,
good for your health.
oh, geez, I'm not a doctor, but I'm just like, now that I think about it, it's like, well, at least me, like, I crave salt and stuff like that. And, well, if we're
Mhm.
human beings and we're like, I don't know, between 60 to 80% water, I would imagine we would try to go the path of least resistance while trying to stay together. But
Right.
this is, no, dude, this is getting me to think. Continue, sir.
Yeah, so this is exactly the odd thing, and what's almost remarkable about people talk about how much water is in your body, like 60 or 70% or something. What's actually extraordinary is how little water is in your body. And what I mean is that the biochemist, if I were to like if usually as in biochemistry, like study a protein and say, I'll purify this protein, put it in a solution of water and like run an experiment by shining light on it. And I need to know the concentration of my protein, that solution to know like how it should interact. And these are the experiments I do. Right. But the thing is that my protein is really, really dilute. Right. If I can't get a protein solution to like 30% protein and 70% water without it crashing out in this exact same way as these amyloid fibers do. Right. And so what is like so surprising is how much stuff your body packs into its water while still having everything stay in solution. So not only are like you a ton of water, it's actually what's extraordinary is how very little water that's free in your body is and how everything still works together. It's really hard to make a solution as dry as your body.
I mean, that's fascinating. I'm just saying here, I'm like, I mean, does it have anything to do that, like, our body runs at a particular temperature? And why I would imagine it would have to be, but then you're going
Almost
to have something
certainly.
else. Hmm.
Like
Okay, no,
the
I feel like you're getting into that. So,
I don't actually like to touch on it, but you're like right, and it's because it's like um, proving why life doesn't like live outside of our range of temperatures isn't like a money topic necessarily, but it is like interesting for like philosophy, I think. And I think that the like philosophical side of that we don't like study as rigorously is that the life that we live takes place in a pretty narrow range of temperatures, and it's exactly the same range of temperatures as some really particular water anomalies show up, like that like spin glass cohesion thing. Right? Potentially, right? That's like theory, but I
uh,
hope to like support that.
well, it's a fascinating thing. I'm sure a lot of folks would totally jump on that. But again, we have to follow the data.
Right. And so where the data is like kind of pointing us for this weird like water anomalies here that I told you of, water has like low mass with a strong dipole and this like a desire for this rotational kind of mode of motion, is that when water is diffusing through itself, so earlier was showing that it's like anomalously slow. And so in this anomalously slow diffusion that hints at these really strong bonds, and is that this transfer of rotational energy between water molecules. So like how does heat and how do pressure waves and how does everything move through water? Right. So the idea is that this is a image that is from like Conway's Game of Life, which is this physics game where there's these rules where each cell, if there's three black cells around an empty cell, then you or yourself are like going to decide to become a black cell. And so it just
It's a
postulates
cellular
through
automata. Yeah.
exactly. And so this could be seen as you can transfer energy through your hydrogen bond rotation faster than the water molecules themselves can move through water. Right. And so a weird and cool thing about having these hydrogen or these like islands of kind of weird water stability is that you can transfer the hydrogen bond rotation energy faster than the molecules themselves can move through the like frames. And so in this way, you could have like this could be an
Can
enzyme.
you say? I'm sorry. Can you say that one more time? I'm sorry.
So the rotation of the hydrogen bond can be transferred from one water molecule to another molecule without that water molecule itself actually moving. So in this way, you can transfer the information of like bond rotations and distances faster than the water molecules diffusing themselves. I can imagine. And this is kind of just an idea that's out there, but it like poses a different idea of biology. Like as opposed to particles running into each other, these particles are like making this like water field that can actually transfer the information like faster than the actual molecules themselves
They're
move
they're
through.
they're talking faster than they can travel.
Yeah, exactly. Right. It's like it's what this leaves room for, and it's kind of like an interesting idea.
Oh,
And so hydrogen bonds are interesting because if I like this dotted line kind of puts the bounds on the electron clouds for water by van der Waals forces, the hydrogen bond is actually like 15% closer than this field allows, and this allows for some like charge transfer. There's actual like electron shell overlap, right? So this is kind of like a quantum phenomena, and water likes to have four neighbors. So you have a central water molecule and it's a hydrogen bond with two hydrogens that can donate to others, and its oxygen can accept two other hydrogen bonds. So you can have two outgoing and two incoming. And this makes this tetrahedral arrangement. But if we were to do perfect spherical packing, like ideal spherical packing, then what you actually get is not four neighbors of tetrahedral, but you get it's 12 neighbors, right? Three on top, six around, and three on the bottom. And so hydrogen sulfide's crystal structure actually has these nearest neighbor packing, 12 nearest neighbors versus oxygen water, which has only four nearest neighbors.
so that is that like almost like a dodecahedron or something?
I forget what this would expand, or do you mean the 12 nearest or the four? I
Yeah.
forget.
I'm just for the 12 nearest. I'm just thinking. I'm like, if I was to act, because I played Dungeons and Dragons, so I'm like, oh, it
Yeah.
sounds like a D12.
It sounds like I wouldn't know actually, but yeah, you have the right like thought. It's gonna make some shape. Uh,
Okay.
and the interesting thing about this is that the because it keeps fewer neighbors than the ideal packing of 12, 4 as opposed to 12, then this kind of implies this like expansion upon freezing, right? So as you idealize your bonds, you actually gain volume and space. You like invent vacuum in your crystal structure much more than if you just packed perfectly, is what I'm trying to say. Right? So this
Can
is again why I'm like,
can you parse that a little bit? I heard the words. I
yeah.
understand what the words will lead to. How do we get to that action?
Right. So as you take liquid water and it goes from kind of like, again, a lot closer where all the water molecules are just moving over each other, they can be a lot closer. They can be closer to this kind of ideal spherical packing. But then when you cool water down and you optimize for perfect hydrogen bonds and you form this tetrahedral shape, to make that shape perfect, you have to expand in size and have fewer neighbors, and that gives you this like expansion of volume that will cause your ice cube to float, right? This is where you like hide that, and so in essence the molecules move farther apart when you freeze and organize, which means that you're like making a higher percentage of vacuum in an ice cube than in liquid water, right? Does that make sense? Right.
Oh yeah. I'm just going on the Wolfram Alpha. I'm just checking. I assume it would have to be like the volume of like a tetrahedron or dodecahedron or something like that. I just because if I see that, okay, blah blah. Yeah,
It's like if I filled in all the electron clouds of all these things, but then the space in between them that's unfilled by electron cloud is like the vacuum that you have in your solution, right? You will have like these little pockets or defects, and in ice you have a lot more vacuum than if you have like liquid water. It's just like a lot more hollow, empty space.
cool.
And yeah, so if we're looking at the like energy well, and what this is this R here, the x-axis is the like potential energy, and so the y-axis is the potential energy, and then the x-axis is according to how far you are, the radius. So if we have like an ideal gas like argon, there's kind of this like bond between it where it's kind of weak out here, but then here at this like well at this ideal radius, it's where the like electron shells are touching but not overlapping, right? So they get the best kind of chemical bond from here. But then when you get too close and you're overlapping, there's a repulsive force, and so that's this like positive energy that's pushing you apart. Right? So
So the
this is
van
like
der Waals is kind of like the sweet spot, or
bingo. The van der Waals, the bottom of this van der Waals well is the sweet spot for where you're hanging out together, where you get the most. Yeah, you're not like being repulsed, and you have the most attraction. And so this is for like an ideal gas, a single well, but water seems to have this kind of double well potential that gives it its weirdness. And so what that's saying is that for um, number one here, this is close packing. And so it's according to, we'll call it packing makes high density water. So here you're kind of optimizing for the van der Waals forces, but to get closer, you have to like make a bad hydrogen bond. It has to be bent as opposed to straight. And so when you're farther away and you make a straighter hydrogen bond, this number two here, this forms low density water, where you have, again, a straighter hydrogen bond, a larger distance, and it makes for a stronger bond. And so you have about 3.8 bonds per water molecule, which 4 bonds possible. And then the bent and broken bonds of this first energy well, it kind of optimizes van der Waals, and you have a more like 3.6 hydrogen bonds per water molecule. And
so basically, some of the sorry to cut you off. Some of like the imperfections also add to a secondary well, even if it's not completely optimized. It almost has like a crumple zone, if you would, kind of like.
yeah, it is. And so that's just why when we're like, this is where ice is like perfect hydrogen bonds. But if you like start to deviate from that, you end up in this crumple zone where suddenly, because you can't get an ideal hydrogen bond, now you're optimizing for like van der Waals. And this is that close packing crumpled kind of configuration. Yeah.
Oh,
And so
it's
this is,
fascinating.
yeah, the likely like energy well of water that is accounting for its weird properties is because there's this fight between optimizing your hydrogen bond or optimizing like packing.
Mm.
And so this kind of leads, I have these like here to, again, try to illustrate more like ideal packing, and then a broken or bent hydrogen bond for high density water. Yeah. And so here's just a plot of some ice densities. So normal like hexagonal ice is the density is 0.9, lower than water, which is 1. But most other ices are like 1.1 or above. And so what's really conspicuous is this lack of ice densities of known ice structures at 1, which is water, right? Liquid water density of 1 at room temperature, about give or take some, right? So we don't really have like a crystal structure of ice at the density that liquid water is, which kind of means that we don't really have a structure of liquid water. It's hard to like know what that looks like. And only recently is it like becoming really apparent. But what all this information kind of sums to is that we now can potentially think of water as a mixture of this low density and high density liquid, and that these two density liquids, they coexist and they're rapidly interchanging, right? And so what I mean by this is that if you form this stable, coherent island of water molecules, because it has to like increase its volume to optimize those hydrogen bonds, that's then going to exert this pressure out, right? And then because it can't exert that pressure out so far, you can only get really small islands of this, and that you can transfer this island stability of this organization of the hydrogen bonds faster than the water molecules themselves, right? So these molecules can like not be in this cluster anymore. You can like rapidly turn over. And so at least this idea of water as two liquid states that exist simultaneously and like self-neutralize each other constantly at very, very fast time scales is one way to then model liquid water that takes all of the what I've shared with you into account.
So water is water, but it has the ability to do like it almost seems like it's like a two-state solution.
Yes. So this is the true like anomalous property that seems to make water so central and so unique to everything else, is this like two states that it's composed of. So when I was talking about like phase separation earlier, like water and oil separating, or vinegar and oil, you had a mixture of molecules of two different kinds of molecules, water and oil. and that they both go find their own home. And this makes sense. But imagine a situation where suddenly one solution of one molecule, water itself, now gets to the correct temperature and pressure where it just nopes off into two different phases of itself, right? Totally paradoxical and wild, right?
It's funny you mentioned that because we went over at engineering community night at Utah State like a few days ago, and they had a bunch of folks, and they actually had some water and viscosity folks there. And it's like,
Mm.
all right, so it's like you got your water in your cup, and cool coloring. I chose the red because it looks really cool.
Mm.
And then you throw some water or oil on top there and everything. It's like, all right, here's the magic trick. Pop off half a Pepto Bismol, drop it in. It goes down, it starts to percolate, pressure change, and all of a sudden you see this cool whirlpool of it like spinning up there and going around like a lava. I thought it was neat.
Yeah. No, it's just fascinating. I wish that there was so much more like science demonstration. Like it's totally water is like the perfect place for this. I feel like I'm excited to one time do like water demonstrations for classrooms just so on hand.
Dude, it's a fun thing, and you don't need much. It's
I
very
know,
inexpensive. We get more people into science and everything because that's my big thing. If you're going to spend your attention on something, it's
right?
would you want to be the coolest things you can? And the
It's
one thing
totally
I know,
true.
water is pretty cool.
Thank you. Yeah, no, I tend to agree with you, man. And so,
Carry on.
thank you. So we're met with this idea of water as like two existing states. And so that's one thing where this low density water, a characteristic of it is it has this increased volume, but it has lower activity. And what I mean by activity is chemical activity is a likelihood that like me as a chemical molecule will rearrange and change my bonds to a new thing, right? So if I have low activity, I'm not going to rearrange my bonds. And if I have high activity, I will. And so a glass of pure water has very high activity. You can put so much stuff, like I can dump so much sugar, salt, anything into it. But you add enough
And
sugar
that's
and
how
something
we would get a super saturated solution or something. Okay.
bingo, which is like a solution with very little water activity, right? There's no ability to form new bonds and take stuff on. And so this is also why jam is a preservative, right? You can put so much sugar into that water that no longer can bacteria like grab water for themselves, right? And that's why it's preserved, right? They can't get
Probably
the
the only reason I've survived the past 5 years, like being single and stuff like that. Like I eat peanut butter and jelly sandwiches all the time, and I'm like, I
yeah,
don't
nothing
always
can grow in
remember to put
me.
it in the fridge. I usually do, but I question myself and give it the sniff test. So
Yeah, nice. And so that's exactly it, right? Like when water can't make like new bonds, you can't make new life, right? You kind of have to like run down this hill. Um,
it's fascinating.
And so in this way, then it becomes really chemically important to have these two different states of water with different activities because your different activities tells you what kind of chemistry you like to do, whether you like to like interact with one kind of thing or not. Uh, and yeah, there's a few ways that water moves. I forgot what's in that. So now there's a few ideas that like I told you that water might be composed of these two different density solutions. One that's a high density at like 1.1 milligrams, one that's a low density at zero point 0.9 like normal ice, and that like liquid water is somewhere here in the middle, but we only have ice structures for these two extremes. So maybe liquid water is like a mixture of these two, right? But then this kind of indicates just like a few structures, right? But it turns out when people run simulations on like a reasonable number of water structures and then done machine learning on that, as they did in this paper recently, titled Liquid Water Contains the Building Blocks of Diverse Ice Phases, they find like a wide range of possible theoretical, like computationally. So as opposed to having these like 2 points,
15,000. That's almost 16,000 phases of ice.
yeah, that are like reasonable, right? And so
Wow.
what water becomes is likely many to an infinite number of ice structures that are rapidly interchanging with each other. And everything you're doing to water is changing your preferred ice structure, like quadrant that you hang out on, right? Like what kind of
Incoming lattices.
bingo, right? And how they talk to each other, right? And so now an enzyme in the body might not be like doing a chemical reaction as much as like tugging on the lattice of water around it to do its thing, right? It's totally wild biology that we can imagine with this.
I mean that's fascinating. I mean, Fractal over from the Wolfram community is talking about signals traveling faster than the medium of particles. Is that like kind of like the wave done in the? I love doing those things. Those are fun.
Bingo. And it's exactly that, right? That's exactly what I'm talking about. Is that we're transferring this like idea or this like momentum thing. Yeah.
I can't run around the stadium that fast. Full disclosure.
Full is that's fair. And so what I'm arguing here is that as opposed to having these like two set like densities, it's likely that we kind of have these like continual like smears, right? Like a large like number of accepted ice phases, and your different like pressure and temperature will set this like ratio of the two like low density side to high density side that you prefer to hang out on. Is like one way that I can make a model, or that people have post models that captures all of this anomalous information, is to invent two basic phases, and they are not like well defined. They're kind of fuzzy, many thousands of possible ice structures that are rapidly interconverting with each other to communicate by this like rotation of hydrogen bonds. Right?
Cool.
So then, yeah, different temperature and pressures, I just have a different ratio of these two phases to each other, would be one way to explain this like difference in volume by the different temperatures. So
could you go back and just kind of like just break it down for me, just because I'm like I can kind of see it. Okay, so if it's higher, the water's going to be a bit more around. Lower, it's going to kind of start to like come together.
Bingo.
Okay.
That's exactly it. Yeah, you start to get these like islands of cohesion kind of that would like move around. Yeah. And so then we're wondering like how fast does water diffuse? And this is something that is a model proposed in 2006 from Computation. But basically, if I like use some measurements and kind of break this down, where in water, the hydrogen bond rotates faster than water translates. And so the hydrogen bonds like change their form and break about up on the picosecond time scale. And then it takes about like 10 to 12 picoseconds for like water to diffuse. And so you basically like, let's say it takes about 12 seconds to diffuse the distance of a water molecule. So that'd be going from like one point on your graph to the next point on your graph. You're going to form and break 12 hydrogen bonds on average for every time you like jump over one, right? And so you're constantly forming and re-breaking hydrogen bonds like many times faster than you are actually diffusing one step to another, is the first thing. And so then how do you actually like do that diffusion? And this is where this rotational jump model comes into play. And so this is how the this is from a 2006 science paper that's been kind of proven. So this is computational, but it's been kind of experimentally supported since then. But the idea is that if this water molecule number one wants to diffuse to our right here, as it's trying to go with this arrow, it's got these two hydrogen bonds holding it back. It just can't go and overpower those two. So it's got to let go of one, right? So this guy above it is going to rotate one of its hydrogen bonds down here, or it's going to rotate in a way that then can accept. So now this hydrogen bond is split, called bifurcated, between these two water molecules. And so because of this, this is like a transition state, right? This is a high energy, uncomfortable place to be, sharing your hydrogen bond. And so it's going to make a choice, like go back here. And that's, again, like for every 12 hydrogen bonds you like form and break, you only like move forward a little bit. Usually you go back, right? But occasionally you go over to the next guy. And when that happens, now this guy is still like satisfied with his hydrogen bonds, but because that rotation, you've now let go here, right? You've let go and broken this hydrogen bond. So now you're free to move forward to the next spot, right? And so this is kind of this,
it would propagate.
Bingo. And so this is kind of this origin of this really slow diffusion, right? You have to like break hydrogen bonds in the right way to allow you the degrees of freedom to go forward and then reform. And so you're constantly reshuffling these ice structures in liquid water. It's like by this.
So that's why water kind of sticks together.
Bingo. But yeah, you're always trying to keep these like ideal hydrogen bonds, but not being able to form it quite ideally. And it turns out, yeah, people like see this. And what I'm really trying to say here is that what this paper is saying, there's this collective burst mechanism of angular jumps in liquid water. And so they're saying like in this window that they're observing water, where you see a strongly like highlighted water molecule is where it's had one of these large angular jumps, and that they cluster together, right? They're here, they hang out together. They don't hang out here. So these bursts of diffusion happen in certain places. And this happens to actually be where the water, low density water shows up. So this is actually your density or a function around you. And then this is kind of like the volume. And so at places where these huge jumps are hanging, these like bigger than 60-degree rotations of the water molecules, they're happening in seemingly lower dense areas compared to the average water box. right? And again, this is interesting because like because of these like islands of stability, if you like kick the bottom card out of a tower of playing cards, the whole thing like crumples, right? And so it's those islands of stability that like enhance the diffusion power of this like chemical bonds, right? Because when you collapse those, that's when you get this huge jumps in motion, right? Is collapsing those like hydrogen bonds, right?
So 60-degree rotations. I mean that if we add that up, that kind of sounds triangular.
It kind of does, and like you can look into this too, and it's tetrahedral and like all these things. Like it's worth looking into the geometry of the bonds. That's not where I like spend my time, right? But where your mind jumps, I think, is a totally like worthwhile research place to like hang out and be curious about. And I'm not quite sure why he chose 60, right? Yeah, agreed. And so this is probably how water diffusion happens, is this mix of like, yeah, this rotational jump model with playing with all these ideas.
So
Uh,
could you just go back at like the yellow and the red? Like what is?
um, this is a figure from their paper.
Oh no, no,
And
angular swing, low patch density. Okay, no, okay, I didn't read the
yeah,
labels.
yeah. So around the areas where they have low density is where they see the high angle jumps show up. And again,
So
yeah,
the low density would lead to angular
fast,
swing that would propagate throughout the medium.
exactly. Like faster, more
Cool.
commonly. Yeah. Uh, so what I've kind of shown you here, hopefully, is yeah, gone over these water anomalies, how we turn them into this idea of a two-state water of water, and how that diffusion happens by this rotational jump model of reorganizing the hydrogen bond network, and how these guys are all like talking to each other in this curious way, right? So what I haven't done is put anything in water, right? It's just water alone. Right. So now the next thing is what happens when we're like putting stuff into water, and I'm going to be arguing that it is going to be distorting or altering the water through like a change in osmotic pressure.
Mhm.
And this here is a protein. So I'm kind of showing like this here is a protein molecule that I have a cartoon of. And so it's going to be in a water solution. And so this here is also a YouTube video of a protein molecule buried. And we're looking at the water here. And so if they cut away, or so if we look at the shell of the most closely bound water in blue here, the waters that are touching, they're moving the slowest, right? And then what happens is that when they expand the shell to um,
Move everything out.
everything out, then these are moving much faster. So the farther away you get from the protein, the faster the water motions become, right? And this is relating back to this idea of chemical activity, right? So the water touching the surface of the protein is really low active because it's bound nicely by the protein, and it doesn't. It's hard to like move away. Right? It's hard to form new bonds, so it's hard for it to shuffle away. Whereas
And as
now
you
when
get
you're
larger, the surface area would increase, and charge tends to be a function, or at least related to surface area.
yeah, it falls off, right? And so you really quickly return back to like normal liquid water activity away from this, right? So any surface you do is going to have this kind of this thing. So that's why I have this like dark water showing lower activity. This water on the protein is less likely to form a chemical bond. And then this water touching the container's edges also, right? Like this is like the meniscus in your glass where the water's climbing the edge, right? It, so uh, if anyone's heard of like exclusion zone or easy water, this is like Gerald Pollack's thing, and but it's this thing where he can put a gel in water, and these little micron beads, micrometer sized beads, they don't enter into this exclusion zone. So there's this gap here where he put this gel into water, and he's got these beads hanging around, and it just doesn't go near the gel. And so he can put this gel in, and you can see it here is this clear part in this solution of dye. And you can see that this dye moves away from the gel surface. And what that's kind of telling you, again, is that even something so small as a molecule of dye that's on the same order of like the water molecules can be excluded by this exclusion zone water formed on these surfaces. Right. So when your water is touching something, it's doing something that changes how things like to move through it, right? On the basic level, like what likes to be around it.
So is this something related to like the flow of the water, just the water? So like just to reiterate, this is pure water we have the poly crystallite gel there, and then you
Yeah.
put some beads. So does it seems like water almost has like, is it like a membrane mentality or?
So I think what's actually going on is that this gel is composed of like some molecules with water diffusing through it. This exclusion zone is composed of water with water moving through it, and these beads are composed of water with water moving through it and some beads moving through it. And the thing is that the water moves through all of these, but the beads won't go next to the gel, right? And so the chemical surfaces that the beads like to hang out and tell the water to do, the water in touching a bead is really different than the water touching the gel surface. And so those two won't
So
talk to
so
each
so we're
other
going into those density in the okay, because it
because
happens
it's
to
like,
have that like
right, it's a
two well
communication,
solution.
right? It's almost like the communication of the hydrogen bonds, like being the thing that dictates, right? Like the water can like bounce around slowly, right? It'll like move through everything, but that like you make these neighborhoods where everyone who likes to hang out together, right?
I,
Uh,
I, I'm still working on the physicalized aspect of it, but just the communal aspect, I can grok that,
All
man.
right, all
So
right.
no, continue, man.
We're yeah, it'll become more apparent as I like flesh this idea out. And so what I'm kind of telling you is that like the surfaces that water touch like change it, and this like really matters for there's these proteins antifreeze proteins which actually stop like water crystals from forming in the cells of things like this snow flea which lives on ice, right? So you might be in danger of forming ice crystals which will rupture your cell membrane, so you will effectively die, right? And this is hypothermia, or right,
That's why
like
that's why freezing people, unless you could literally instantly we're kind of screwed
that's
there. Because I
exactly
remember Professor Wolfram has brought this up a couple of times, but apparently I think there are also maybe some frogs or maybe some. I think there are some frog
yes.
species that. Okay.
Yeah, yeah, and there's different ways to do that. You don't, not everyone's using proteins, but proteins themselves are one way of overcoming this. And there's also the opposite. There are ice seeding proteins that might be in a bacteria that wants to infect a plant. And so it'll be on the surface of the plant, freeze an ice crystal in a thaw, and then that crystal will break its way into the plant so then can enter and like reproduce, right? And
That's
then you can
crazy.
right, so you can then take this bacteria with this ice seeding crystal and then like put it through a snow blower into the air, right? And just seed, or like you could like do something like ice or cloud
He
seeding.
just spread. Oh my God! He's
Right. So
spreading around crystals that are attacking the plants.
exactly. So theoretically, a
Wow.
lot of like cloud seeding is actually done by microbial life floating around the atmosphere, potentially. That would like, yeah, seed nucleation, rainfall water.
I don't know.
Um,
It would explain a lot, and I like how you also say that you're giving good caveats there. Like a good, it's very easy to say this is this, but then I'm kind of on the mind of the generation where I tend to be raised where it was like only Sith deal in absolutes.
yeah,
Now, I'm not saying that that's a hyperbolic statement there, but I think it's because
yeah.
science is the process of figuring out what we don't know.
Right. And I'm very much with you because oddly, my journey the past 3 years was not started by water, but so much as like an interest in UFOs. Right. And the consequence from this is this like thing of when we use our language to be like, that can't happen, it just sets up a prison wall, as opposed to like, under these conditions, it's unlikely. Right. Just by like changing our
Yeah.
language, we allow for more stuff to happen and show up. And it's so important. So I really try hard to couch my words in a way that's like allows a lot to be existing,
No,
but
no,
not
no, no. I love no. The same thing. One of my friends who pops onto the Cosmic Council when I occasionally hold it, Brad Voorhees. He works for the government and everything. That's a former military guy. He worked for the Navy and everything. And at one point, he had always kind of been interested in those things. And he's like, well, at one point, the Department of the Navy came out and said, yeah, UIP, yeah, this is a thing. And he's like, that's hey, I work for those folks. If they're gonna say that's a thing, he's going and he's trying to work these different anti-grav drives and everything. And I'm saying, hey, power to him and everything. It's like I listened to him. I came across him along the Theories of Everything community. Shout out to Kurt there for helping me meet a lot of very interesting folks. And it's just one of those things. It gets people excited and getting folks excited about science and just wanting to build cool things. Come on, who wouldn't want to live in like a Star Trek world and stuff like that? I mean, that sounds fantastic. Go explore the cosmos.
right? Easy sell. Yeah. And so
Yeah.
I like
So
trying
let's
to
get to there
like,
through water. Let's
yeah.
do it, man.
So so proteins, this is an example of how an ice binding protein might manipulate structuring water around it. So on ice antifreeze proteins, there's an ice binding surface that is going to face the ice, and then there's a non-ice binding surface which will face away. And so this is a paper that did computational studies to show that ice binding antifreeze proteins seem to structure low density water around the ice binding surface and then prefer a high density of water around their non-ice binding surface. And this is actually going to be what's going to rotate the protein to face the ice crystal and allow it to interface so well with the ice crystal, is because the water that it structures is going to be much more like the ice, right? And then it's this like cloud of high density water that's going to keep it, right, like facing oriented to, and then keep that ice crystal from growing farther. Right? And
It's
so
kind of forming like a bit of a shield there.
exactly, right. And the idea is that it's got this one side that likes or structures, promotes water to like hang out in that kind of a way, and then this other side that will like break down or not be compatible with the ice structuring of water.
Because water tends to stick together. And now, do we have anything on like the ratios for like those proteins at all, or?
Yeah, this is actually a paper. This group, or I rather, some of these students have actually looked at this different ice binding proteins from different species of different potencies and different things like that, and then try and figure out like what's the driving force. And it turns out that all ice binding surfaces look kind of the same, and so you don't get anything from that. It's actually the non-ice binding surface that, right, is like the interesting one that's promoting the differences.
The water continues to be water, but that's cool.
Yeah, yeah. Uh, it's all I love this like little story of these proteins doing this and like playing with that. So I
That's a
think,
fascinating observation. Continue, sir. Sorry.
yeah, thank you. I'm not sure if I want to. I need to chat about this stuff, but this is some more like hard, like some common biochemistry stuff that I typically like go through quickly. But I think that these terms wouldn't be as familiar to this crowd. So stop me and ask the questions as they like.
I don't know what anything there means.
Bingo. Yeah, this is pretty nebulous. So the biggest thing so the first thing I'm going to talk about is up here in the corner of protein naturation and denaturation. And this is kind of what I was talking about when I studied neurodegenerative diseases like amyloid diseases like Alzheimer's or Parkinson's. At a certain point in your life, your proteins are happy, they're nicely folded and functional. And that's what this guy is, a nicely functional folded protein. But then they unfold and they form these protein fibers, or they don't work right when they're unfolded. And that's this denatured protein. Right. And so this general concept is that proteins are these nicely folded tiny machines. And if that they fall apart and unfold, they just become spaghetti strands. Right. And yeah. So health is kind of keeping the right structure at the right time. But we can do this thing called denaturation, where we cause it to fall apart. And that a scientific observation in biochemistry was that certain salts would be better at stabilizing the functional protein or like denaturing it. And because of this trial, like when I say functional protein, I mean folded protein. There's also many unfolded proteins that are functional. It's just kind of like sometimes things are meant to be together and sometimes they're meant to fall apart, and going in and out of those cycles is important to life. And so it's not like all proteins should be together at all times, right? I don't want to invoke this kind of idea.
As somebody that used to work at a gym and work out for a couple of hours, you don't want to have too much protein. At least based upon my observation of that, and just I feel like at least me, like I'll crave salt. Like if I don't have anything salty, and like it's been a while, I feel like I need some of that and some water and everything. Like I feel like more hydrated and can do more. Or like if I'm without salt or something like that, just I don't know. I just feel better. I always assume it's like, oh, well, salt, water, this, that. You need this, that much, but then again, you don't want too much. And now, actually, the too much is actually making a lot more sense for what we've kind of covered here. I mean, no, this is explaining a lot. But continue, Mike.
Keep going deeper, and so
It's a deep dive into water.
It's all I do is talking water puns these days unintentionally, but it fits the bill.
I totally support that, man. We're pro dad joke here.
Perfect. All right, in good company. So these proteins, we want to keep them like healthy and to do what they're supposed to be doing. And water and protein levels are important, but also the type of like salt, right? Not just the type of or the amount of salt, but the type of it is what matters. With certain types will like favor one of these sides or the other. So the question biochemically is, why is that the case? And this is actually something that like we learn about this series of salts, but we don't necessarily learn why. And the why is now like apparent in the past couple of decades, right? We kind of like have more information about that. So one of the ways I can look at how
why So why do we know why?
Why do we know why? Is because this is actually called the Hofmeister series after a chemist called Hofmeister in the 1800s noticed that sometimes when his protein solution was kept in some salts, it would stay together longer versus other times it fall apart. And so unknowingly, he would just call it the Hofmeister series. And that's this like line. And then later on, we try and find the similarities and the differences that tell us why they're organized the way that they are. And this similarity, yeah.
So basically, he was the one that initially noticed. This seems to be a very interesting occurrence. Might not have known exactly why, but now we have more information to why that is the case.
Bingo, right? So like this would be taught as the Hofmeister series in college, and we'd be like, we have this like layer of salts, they change protein solubility, like on to the next one, right? But now I can actually sit here and tell you why they're different, and this is so important for understanding like the water stuff, right? And so we got so how we're going to measure differences between these different salt ions is we're going to use this thing called a column. And this column is going to basically be a tube, a cylinder that's packed with beads of Sephardex. And Sephardex is this molecule here, and it's basically like carbon sugars with some oxygens and hydrogens in interesting places. It's basically like an immobilized sugar bead that has, and what is important is that it's got these pores that allow like some molecules in, but not big ones, right? And so what's interesting is that when you have a column like this, when you run things of different sizes down, the big ones run really fast because they go in between these beads, but then the small ones, they run into the beads. And so they have a lot more surface area and volume to diffuse through to get through the column than the big things do, because the big things inherently have less surface area and volume to diffuse through, right? So we can change things based on size. We can purify based on size of how they run through that column.
Can you say that one more? Because I'm trying to grok it. I'm like,
Yeah,
all
yeah.
right, shouldn't the big thing? I would intuit like the small things would go faster
I know.
because you'd have this. But then again, is it because they are small and something charge is holding them up?
It's not the charge, actually. It's the random motion, the random diffusion. They have such vaster volume to play in and diffuse.
That's why lighter particles tend towards lesser pressure.
Mm-hmm. In such a thing.
Okay, so it's more of a factor of mass or mass and surface area.
It's mass and surface area, and we'll get a little bit more into it in a second. But
Okay.
suffice to say, like larger things run faster through the column because they have fewer decision space to like go off in a corner, right?
Okay, so it's like the little ping pong. If you're playing, like if you just have a bowling ball, okay, it goes on the gutter, it hits some pins. Whereas if it's a pinball machine, it bang onto this thing, plop onto this thing, go all over, and then you might not even be doing anything. It's just kind of a little bit of a probabilistic view on things, yeah.
Exactly, and so it takes it so much longer for that small thing to find its way to the end of the column because it's got so much more to like travel through.
It's got more things it can do.
Yeah. So in this way, we're looking at how long it takes these things to like move through this column. And so this is kind of a visual representation. So here is how things come out of the column. So this fraction is basically like time, stuff coming through the column as it comes out. We're reading it out. So THO here, this stands for tritiated water, right? T is for tritium. And so this is basically how long it takes a water molecule to run through the column. Is it going to put like a pulse of tritiated water on top and see how the tritium comes out the bottom?
Can I ask one real quick question?
For sure, C's.
Is that TH0 or is that THD?
It's THO for tritium, hydrogen, oxygen.
Okay, cool.
That's,
I have to ask. I apologize. This is a monastery-related question. Do you know anything about the T and P transfer process when expressed in HD or HT?
No, I don't. So I don't know the exchange process. I don't know a few of the phrases that you threw at me. So you should explain the overall thing to me real quick.
No. That's what we're literally trying to come out because there's things in HD we literally thought they were like Henry's Tesla and stuff like that, but apparently it has to do something with hydrogen and deuterium and tritium. So I'm sorry, I had to ask.
So there's different kinds of water. So first of all, hydrogen and water is So that's there's H2O, just two hydrogens and water. There's HDO, which is just hydrogen, deuterium, and oxygen. And so that's one of your hydrogens that's replaced with the deuterium. And then there's D2O, which is deuterated water, heavy water, where both hydrogens are replaced with deuterium, and you have the same degree of freedom with tritium. And so this means that when you have isotopes of deuterium or tritium in water, they're always being exchanged between water molecules. And it's rare that you have so if you have 1% tritiated water or deuterated water, at first it might be like D2O, but after 10 minutes of lying it in there, it's exchanging all those Ds around, right? So it on average becomes HDO, right, as opposed to D2O. So each of these HDO, H2O, D2O, THO, they all have different chemistry because of that different hydrogen having a different impact on the structure around it and the different transfer constant. And so each of those has its own reaction rate for how it exchanges with another one. And this is where those differences will come up in ICES, right? Because you have ICES that will have ratios of this, or solutions will have explicit ratios of those.
Yeah, because I'm sorry to do this. I just have to show you this. Basically we're trying to figure out what the heck this is. I'm not sure if you recognize any of those numbers. That's 2.0200 times 10 to the negative 8. And we're talking about shielding differences of D and P in HD. I don't know if that means anything to you.
Okay, not a ton, but it sounds like because I usually deal with water, but is this a pure hydrogen, or is this hydrogen in water?
I think it's hydrogen deuterium, at least so the reference paper from 13 years ago.
It is. It's referencing hydrogen and deuterium. Yeah.
So some relation between those. Okay, because we've been trying to figure out exactly what the ratio was. If anybody knows, please let us know. But okay, sorry, sidetrack.
Yeah, we can chat about that one in the future. And that there's some stuff I might be able to help there very, very loosely.
No. I saw things that were related. And I'm like, wait, should we be looking for HD0? Maybe that would actually help us, because that was the first time I saw that. So
this stuff is related because deuterated water has a different freezing point than hydrogenated water, and this matters, right? Because it's changing the crystal structure, and because of the shielding of the protons, it changes the quantum nature of the hydrogen bond.
I'm not sure the accuracy of this, but I do kind of like what Kali is saying. We should think of water as hydrogen liquid and oxygen kiwis in a specific ratio. I do like kiwi. I get the gist of what she's saying, because it kind of looked that way.
Yeah. No, that stuff matters. Yeah, it shows up.
Continue, sir.
So what I was at was we're looking at how different salts and molecules are going through this column. So this sets the baseline for where water comes out, and this chemical dextran is just a big sugar. Consider this a really huge thing, and it's just going to be the first one out of the column because it's the biggest, right? So now we have something that's unimaginably large compared to water, and something that's basically water to set our range for where these salts will go through. So now I run fluoride through. So fluoride, very densely negatively charged. And what I'm showing here is that because of this charge, water is going to point its positive side, its hydrogens, towards fluorine. And what this translates to is effectively about 2 shells of water molecules around fluorine are strongly oriented and bonded to it. And so fluorine, its presence itself, and it affects about 2 shells of water outside of it. And this gives it this really large, apparent size. So that's why fluorine, one of the smallest, again, atomically, the smallest one that they're looking at, goes through the fastest, right? Because its apparent size, because it distorts, it always has to keep those 2 shells of water around it. So it's not going to go deeply into that bead or whichever.
So are we talking from a molecular level or a bond level? Is it actually could we imagine in my head, we take fluorine, okay, we got a layer of water molecules encasing it, and then another layer of water molecules. Is it like that?
Yes.
Okay.
Yeah. And so the thing is that if you want to interact to get to the juicy fluorine center, you have to rip off one shell and then the other shell. That's really, really expensive right?
So you got to go through a double cover of water in order to get to the
Right.
fluorine.
And so
Cool.
for this reason, fluorine doesn't like to like fall out of solution or interact with the like beads, right? It just likes to flow through because the water is always going to be like having that shell with it. And so we call this like the hydrodynamic radius, right? And it's much, much larger than its molecular radius. It's a really small molecule, but it has a really big apparent volume moving through water.
Right? Well, things can have quite an effect. Cool.
All this like tends to really matter. And this is what's so fascinating is that when I was learning biochemistry in college, it wasn't taught this way. So we didn't appreciate that it was just dramatically different.
Dude, like I said, it's like I'm just like, oh, why would I want to go into that? And it's like you hear, like, because I like power plants and stuff like that, and using it for power, and like, I mean, that's always fascinating. It's like these are just a whole bunch of cool little things. Just even just mentioning, yeah, this is
Right.
really cool. It's like gets people excited. It's getting me excited.
Me too, and I'm glad you feel that because when I started learning about this, like, oh, this stuff makes sense. Right before it was just like facts, but like they talk to each other, right? There's like a system and a network here of like how this information is like talks to each other. And again, that like mystery in the 1800s of why certain salts change proteins and stuff, right? I mean, I'm going to tell you why that is. You'll be able to like answer something that 150 years ago was we had zero idea, kind of.
Cool.
And so then we look at chlorine. So chlorine is less negatively charged than fluorine on its surface. So they both have a -1 charge, right? They both have one more electron than they have protons in this ionic form. It's just that because chlorine is bigger and has another shell of those electrons, then its physical size spreads that charge out. And that's the shade of blue, from being like intensely charged like fluorine to less intensely charged, right? Because that charge is now spread over a bigger surface area. So that one negative charge
for the chlorine.
for the chlorine.
Okay,
So
that's
the one
because of a different arrangement.
because it has an extra shell of electrons, it's just bigger. So that negative charge is spread over a larger apparent surface area.
Okay.
Yeah. So here, chlorine only really has like one shell of waters that are kind of like perturbed by it, whereas fluorine have two, right? So now if we go farther along this scale, we go to like bromine and iodine, right? So these are bigger. So they have, again, just the one negative charge, but spread over an even larger surface area, right? And so if you notice iodine shows up way, way late. So it's the biggest molecule that they're looking at by like side. It's the biggest salt by its radius, but its hydrodynamic radius is the smallest, right? It spends the most time trapped. It's even smaller than water, right? It takes longer for the iodine, which is bigger than water, to go through than water does. And this is ostensibly because this charge is spread over such a large surface area that water is no longer attracted to it. It's actually kind of repelled. Water would rather interact with water than this like lame charge, right? So this actually means that water will push it out of itself, right, onto the surface of the beads over being carried through, right? And so in this sense, it runs faster or longer than water because water runs through it faster because it's actively like kind of pushing iodine out of the solution. It would rather that iodine wasn't in water. And this is like the hydrophobic effect, like why butter or fats aren't soluble in water, right? They're not charged enough. They're not interesting enough to attract the chemical bonds of water. And so they get pushed out. Right.
I mean, no, that brings all types of questions. Because before I was just like, well, it's just all less dense things. And it's like, all right, well, but this is a smaller thing, but then it has an effective charge and everything. And so why do these different things happen? And just all I know is Mr. Wizard got me into this stuff when he took that potato and let's throw a little salt into some water, a couple of cables, and he turns on a light bulb. I'm like, you are a wizard, my friend.
Is as advertised. It's perfect. And I think that's what's like curious to me. It's weird. It's like whenever we're talking about water, it's always like inverting the expected, right? And again, it's always that's like an interesting thing where it keeps like being this like weird inverting thing.
I hear inversions are important. So.
It seems to be. And I showed you this for like negative ions, but the same thing shows up for positive, like lithium, because it's really tiny and charge dense, huge hydrodynamic radius. And then as you get bigger, like sodium, rubidium, cesium, and then down to hydronium, or just like an acid, you get smaller, right? So this holds true again for the other side. So what I've been, but this is what's really interesting here is the difference between sodium and potassium, right? And so sodium and potassium are really interesting salts because of basically our cell biology. And so do you ever cover the action potential and neuronal impulses in any of the biology classes?
I have no idea what those words mean.
Okay, so when
There's
you
something
have,
something rotation.
yeah, let me see if this is what I want to get. So if I am, so what I'm looking at here is solutes change the behavior of water nearby. And I was kind of showing you by like that fluorine like really attracts the waters, and then iodine actually kind of like repels the waters, right? So what I'm looking at here is neutron scattering, and what they're going to measure from this neutron scattering is they're roughly going to get an estimation of how fast water is diffusing, how far water is diffusing. And so they're
So
going
we're
to change
measuring
this.
the diffusion of water using neutrons.
Yes, that's correct.
Okay.
And what we're going to be looking at is we change the concentration of salts in the water, right? And so what the neutrons show us is that at bulk baseline, we set the baseline diffusion of water. And so what we're really saying here is that if there's this water in red and it's deciding whether it wants a hydrogen bond with this guy or the guy on the left, that they're both like kind of equivalent. And this is saying the base for how fast diffusion is occurring, that there's no preference between these two. Or no real preference.
Quick question. What is the baseline for water? It's like between 2 and 2.1?
Yes, yeah, to like 2.05.
Cool.
These dimensions don't mean too much inherently to me.
Okay, yeah.
It like is physically accurate, and you can like look into it as a scale.
Okay.
Yeah. And but it is like diffusion apparently is measured in surface area. I find that kind of interesting, right? Because it's a 3D.
See, that was my question. I apologize for not saying anything, but it's a practical thing because I remember looking at like some of the Maxwell equations, like charge density, charge, and volume, and they kind of say those words, but when you actually look at the Mr. Sci folks had was it Physics with Kathy, and basically she goes in. It's actually expressed in like surface area, like square, not cube. And I'm like, that's very interesting. I still need to look more into that because charge is just, I don't know, it's one of my things. I'm just fascinated how it works.
So I'm with you on this. I'm just now at the phase where I've like come across this information and I need to like physicalize it. I'm like, wait, why is this squared as opposed to something else? And so I don't have the answer for you right now, but probably has to do with how you have to like actually measure diffusion of like one particle, and it's like diffusing over its like a visible radius, right? If you're like supposing the problem.
In physics a lot of times it says, what's our future light cone, so to speak, or something like that. Yeah,
exactly.
You do all the cool Penrose things.
I mean, that's what we're here for. So we have this, water baseline, and then I'm going to add potassium. And what's odd about potassium is that potassium is one of these like less charged dense ones. So if I put potassium, so if I'm looking at this water molecule and it decides whether it wants to hang out with water or potassium, potassium isn't charged enough to attract its attention. It would rather go to water, right? And so this is like that iodine thing where it's kind of like it gets pushed out of solution. Water would rather hang out with that, but sodium is the opposite. Sodium is charge dense enough where the water would rather hang out with sodium than it would with potassium. So you kind of like stabilize this bond between the two. And so this is low activity water, right? The activity, this water that doesn't want to interact with something else, but interact with sodium, it's lower activity because it's less available to bond again. Right? And so this water that's next to potassium, high activity water, because not only does it like want to bond again, it actually is like incentivized to leave the potassium on some level to like go, hang out with the water. And this tends to actually change how fast water itself diffuses, not to mention these things through water, right? Because we show that when you interact with like strongly with the water shell, you diffuse a lot more slowly than if you interact with like nothing. But then the water that's outside these shells, it also is changing its diffusion. So this is relevant biologically because on the inside of our cells, like inside of a neuron, we keep the concentration, the intracellular concentration of potassium around like 150 millimolar, whereas sodium is like 10 millimolar. So we keep potassium on the inside of our cells, but sodium is 150 millimolar externally. So we keep sodium on the outside, right? And so when you have a neuronal impulse that travels like innervating from your brain down to like a muscle, and it's going to travel along the axon, the action potential is this traveling wave. And what this wave is actually an exchange of the internal potassium for external sodium that is then like moving down the neuron's axon. And this is the electrochemical impulse that is thought and like action, right, that our neurons are doing.
So you have an internal action and an external action,
And so we'll
or is it
internally,
basically just kind of like is it going along the neuron? Because I don't really actually know what neurons are made of. I assume proteins. I
yeah,
assume what you're
it's
telling me here and everything. But
yeah, it's like this membrane. You could consider it almost like a capacitor. You could consider it as many things. A capacitor surface. It's a barrier. It's a membrane that prevents usually the exchange and osmosis of like water and salts. But when you decide that you want to send an electrochemical impulse in the form of like a neuron firing an action potential to then talk to other neurons down the line, where that's then like carried on from one to another, that electrochemical wave is actually the exchange of intracellular potassium for extracellular sodium. And so this exchange of potassium for sodium is then what's actually traveling the distance in your body. And so
so does this almost have to, sorry to cut you off, but does this have to do with kind of like why we're able to respond the way we are? Because if water can communicate via its bond structure rather than just being like, okay, I need to physically go this way, like this is how our nervous system works. Is that bond sharing or
right.
off the?
And so this is normally the point in the when most like biochemists or PhD level like cell biologists would be like, oh, we kind of know that potassium's on the inside and sodium's on the outside, but why? Why would it be that all cells, all life has potassium on the inside and sodium on the outside? We kind of think of them as like interchangeable salts. But because they're different chemistry and interaction with the water around them, there must be a reason why we always have potassium on the inside and sodium on the outside. And so normally this is a really common, the action potential is a really common like thing that we learn about in school that like many biochemists would know, and it's always thought about as like this exchange of salts. And so we think about the exchange of salt but not these water waves, right? And so this is where this like big unveiling usually happens for the biochemists, where they're like, oh, I just been thinking about the salt exchange, but it's really the water difference that's like the physical manifestation of this, and that's like the what I'm trying to like unveil here, right? That's the new thing.
That's awesome. Continue, sir. Yeah.
Yeah, so we mostly think of like the salts themselves as having this physicality. um Yeah, and it's always like it's actually the potassium ion that we're like should be more interested in, because we always think of sodium chloride as like table site, but it's like potassium is like the big ion that we really like need to pay attention for health, and that a lot of athletes might even have under potassium because they sweat so much.
It's well, that's one of the things that Fractal's highlighting. Again, I'm not a doctor or anything, but saying that yeah, I mean, I could see that as a potential thing. Again, go check with your doctor, check your potassium levels and everything. I hear it good.
So,
I feel better after eating a banana.
me too, hands down. And so part of this is why it's not only is you need the ion, the salt, but it has like this physical manifestation on how it moves the water around it. And then this is another part where for a common like biochemistry thing is that we learn how the action potential is propagated. And it's usually through this thing where this is a protein that's the gate between sodium and potassium on the outsides and insides of the cell. And it's usually posed as these spheres represent chemical groups that detect a charge difference. But now we can like reimagine that as opposed to detecting charge by the protein or an electric field, you could actually be detecting the difference of like the water on one side or the other, right? And there are, in fact, issues with our models for how these neuronal transmissions are transmitted, as like thrown out here, saltatory conduction as an electrostatic compressional wave in the axoplasm, because by doing their math, they find out that certain neurons, they can't actually carry that electric field enough to trigger the protein between these gaps. And so there must be something else. And again, it might be this wave of water like pressure that's actually doing that. Right?
So just to pause real quick, Mike.
Yeah.
It sounds like what you're saying is like we have a lot of very successful models and everything, but as we've increased our accuracy and our basically looking at what's actually going on, a lot of what we built, we might actually need to rethink some of our models.
It's exactly what I'm getting at. That's usually the big reveal here for like a group that's always learned about the action potential and like how they see it. Is this is a big unveiling that, oh, there might be a lot of room for interesting chemistry that we weren't appreciating because we didn't know this about water, right? So we jumped this other thing we could measure, which is like electric field, that kind of thing, and then we rated against that. But there is this whole new other way.
So what you're saying, I mean, that almost sounds like it opens up like a new field, kind of like taking like folks from biology, chemistry, and physics and stuff. Kind of like I think back in the day they would do like, let's get some physics people from the IHS and some mathematicians or up at Stony Brook or so, and they have these meetings and like you have like Jim Simons and I think I forget the gentleman thing, Yao is, but basically they both came to fiber bundles through completely different methods and stuff, and you're like, oh, this is very interesting. I just feel like we need some more cross-discipline discussions and everything because we never know what we can learn.
And so this is why I've been so desperate and it's been hard for us to connect, right? Is because I've been writing furiously because it's now becoming really apparent in my field that people are running up against these problems that I spent the past 3 years like reading about because they're the problems I ran up against them 3 years ago. But now it's time that everyone else is like seeing that this is it. And so that's exactly why I'm so like anxious, just everything I'm can to throw out to like get this out there because it is this time where we start to like I've come across like now it's seeming like 3 different groups where none of them cite each other, develop this idea that water is composed of 2 different phases that coexist. I've seen this like 3 different times now, right? And so that exact thing you're saying is that we're like no one's reading and consolidating. We're like moving too fast, so it's time where we can do that. The time's ready.
It's not do I this, and this is one of the things because you kind of hinted at that. I kind of had the idea. My base intuition is I kind of think I saw some of that just even from an outside observer on YouTube and stuff like that. A lot of folks are doing interesting things. I don't think folks are keeping up on each other's work because I hear like they'll go through the interviews a lot of the same questions. It's like unless you're really versed on the deep lore, so to speak, about all of a sudden it's like listening to Stephen Wolfram yak about turbulence for about an hour and then at one point literally say like, well, some of those folks and some of these using superfluidity and stuff like that, we shouldn't be able to replicate or predict results or something like that. It's too hard to recreate. And he's like, if you actually really press some of these folks and they're not being recorded or anything, they're like, yeah, we actually have seen very remarkable results. It's like, we don't know how to explain it. We don't publish it because we're afraid people will make fun of us. And it's like, that hurts. That hurts because a null result is a result. But I'm like, if you see something and it seems kind of crazy, even if you just put that out there, maybe there are other folks that have noticed a similar thing, especially if it's like, well, you're not supposed to talk about this. It's like, well, have we gone through and eliminated the other potential things in our discussion? Have we eliminated the factors? Because at least when I learned science and stuff, it's like, listen, you try to account for things the best you can. Understand there's going to be an infinite number, some may say computationally irreducible, number of different variables you can't account for. Let's account for the best we can and see where the data leads us. And that's why this is so exciting. I just need to ask one thing. Did you want to keep going? Because if we do, I will need to take a pause for a short bathroom break because I just chugged an entire thing of coffee. Or maybe this is a good place. We've laid out a bunch of things. I kind of jumped ahead, and maybe we could do maybe a part 2 at some point.
Yeah, let's lean towards part 2 because I'm loving this and having this chat and like throwing this out there and like full disclosure, I am desperate to get this information out for all the reasons you say, and for me to get these like practices of going through these storylines and sharing with different audiences is really helpful because the overcoming this issue that I'm in this thing where like I chat with bosses who are cutting edge scientists, right? And I'm like, this stuff is insane. Have you been paying attention? And they're like, no one has any idea. And this is the issue because we don't have enough time, right? The amount of time it takes to be a full-time professor and keep current is impossible. You cannot be a full-time professor and keep current. And so usually professors are hired for being current when they're a postdoc or like 40, and then they kind of stop learning or doing new stuff and they just like practice what they had done when they were 40. And so, but the issue is not that we should be hard on these people. It's that their time commitments are so great that they can't like pivot to these new ideas. And
Oh
so
my God! They have so much to do and everything. The
yeah,
grant writing, all this and everything.
all
It takes
that.
up so much time. You don't have enough bandwidth.
Right. And so my biggest contribution, I hope, to science isn't a scientific discovery. It is the world's best picture book. How can I best get you up to speed, right? To reframe all of what we've been doing for the past 60 years and then reframe biochemistry in a much more streamlined narrative to like reteach it so that we can, like, I can spend that time for you, right? I can like catch you up on 60 years of stuff is my goal, I hope, because then we can like re-enter what is it for that big name professor now to have this new baseline, have it really easily digested, and then go from there, right? That's what we need to do is like reconsolidate for the next push. And I hope that's what we do now with like this water stuff with biochemistry. And so it's like great for me to be able to share this story under so many different contexts because I really care about this pictures and this storytelling and getting these ideas across, and all that practice is really useful. So yeah, maybe we pick up sometime in the future and tell you how like salts talk to each other.
Dude, that'd be amazing. Real quick, Fractal is asking,
Yeah.
do you remember Buena Vista and structured water? Was he on this? I'm unfamiliar with that topic.
So I'm unfamiliar with who explicitly you're talking about, but as soon as I got into like the more mystical and interesting side of water, which for me was the Orc OR Roger Penrose thing, because I started to listen to talks about Orc OR, and I'm not a quantum physicist. There's nothing for me to judge there. But the biochemists that they would bring on to support this were sharing this really interesting and coherent like light transfer property of proteins, where they act almost like fiber optic cables for microwaves. And I was like, as a protein scientist, I was floored by this, right? So my interest in the water stuff came from these like weird water observations, but because they were sharing experimental results that really surprised me, not to do with like memory or consciousness, right? But with that, I think that there is like this memory of water, right? Because water, I've kind of shown, has this weird crystal structure to it, and not many liquids have that. They're far more disordered. So water has the ability to have this intense structure and this intense memory. If you think of like, if I just put a blast of like a wave, like it bounces around forever. If I do a wave of changing rotation of hydrogen bonds, that's going to dissipate, but it's going to be there on some level. Can't get rid of that like order. And so what are situations where you might get like this really interesting coherent like switching of like water waves, like almost like a time crystal of like water, and it's like your body and like the natural waves of metabolism might literally be that you build up enough of one water and then it goes out, and this is almost like your cells breathing is like one water structure, another water structure, one water, another structure, and your breathing is doing the same by putting oxygen in and taking it like carbon dioxide out. You're alternating your metabolism, you're pushing all of the nutrients in one way, then sucking them out another way. And these might be like waves of water, but then this is like a time crystal, right? So there's like some implication of like memory there. And so a lot of people imply, and this is where I don't know Benny to say or these other people, I don't know them explicitly, but what I've learned about the physicality of water allows for a lot of mysticism to seemingly creep through quantum effects, right? Because hydrogen bond is a overlap of, it is a sharing, it is like a coherence, it is this weird mystical overlap of like wave functions with them overlapping, right? So I take very seriously this like water memory when a lot of people discount it, not because like, I mean, people know how to be healthy. It's not because you're having not structured water that you're not healthy. It's because we're not eating right and working out and getting sunlight and having like, you know, crazy stressful lifestyles, right? We don't need to like invoke a bunch of like weirdness to get healthier through water. We can just like settle for what we know, but there is like a lot of room for this weirdness here. Right?
Okay. All right. So maybe we'll get, I guess apparently we'll be going getting into salts and how they talk to each other. So I'm here. It might be a beautiful symphony. But hey, Mike, thank you so much for joining us today. I'm
For
gonna
sure.
pop off the stream and maybe we could chat for a minute or two after if you were game. But other
Yeah.
than that, thank you everyone else for joining us. Peace out and